Hello folks, how's it going? Mike coming back at you with yet another video on college algebra. In the previous video, we talked about transformations of graphs of basic and or common functions that we'll see in this course. In this video, we are going to talk about symmetry of functions and functions being even and or odd. So if we're given an equation in x and y, it doesn't necessarily have to be a function, but for the most part in this course we will be working with functions, so that's why we call symmetry of functions. But technically these ideas and concepts of symmetry don't have to happen with functions. The graph of an equation is symmetric with respect to, or for short WRT, the y-axis if replacing minus x for x results in the same equation. We have symmetry with respect to the x-axis. The graph of the equation has this symmetry if replacing minus y for y results in the same equation. And then lastly, we have symmetry with respect to the origin. And this graph has symmetry with respect to the origin if replacing minus x for x and minus y for y results in the same equation. So we're going to see some samples now, some cases where we have each of these three kinds of symmetry. An example of an equation that has symmetry with respect to the x-axis is y to the fourth minus y squared is equal to x. If I replace minus y with y, I have minus y to the fourth minus a minus y squared equals x. And when I raise this to the fourth power, I have the negative 1 to the fourth power, which is a positive 1. And then I have the negative 1 squared here, which is a positive 1 as well. So this gives me the same equation as what I had. Y to the fourth minus y squared is equal to x. And graphically, what symmetry with respect to the x-axis looks like is if you took that rectangular coordinate system, if you took that coordinate plane and you folded it in half on the x-axis, the top half of the curve, or the top half of the graph of your equation, would line up perfectly with the bottom half of the graph of your equation. So that's what we mean by symmetry with respect to the x-axis. An example of an equation that has symmetry with respect to the y-axis is our basic absolute value function. Y equals the absolute value of x. If I replace the x with a minus x, this is just one of the basic properties of the absolute value function. The absolute value is really just what is the distance that a number is from the number 0, and the number x and its additive inverse, or its opposite number minus x, are the same distance from 0. So the absolute value of minus x is equal to the absolute value of x, and thus we come to the same equation as what we had. Similar to taking the coordinate plane and folding it over the x-axis and having the two halves meet up, if there is symmetry with respect to the y-axis, then we can fold the rectangular or coordinate plane over the y-axis, and the left-hand side would match up perfectly on top of the right-hand side. An example of an equation that has symmetry with respect to the origin is x squared equals y squared. I'm substituting minus x in for x and minus y in for y. When I square these things, I'm going to get the same equation. And for symmetry with respect to the origin, what is this doing graphically? Well, if I were to take one half of my graph, say the half that's on the left-hand side of the coordinate plane, if I were to fold it over the y-axis, then take that image that we have and fold that over the x-axis, what I have then would line up perfectly on top of the right-hand side of my graph. Some of these symmetries for these graphs have a related term to them, which we can describe the function itself. And with that, we come to even and odd functions. A function f of x is even if f of minus x is equal to f of x. That is to say, if you take the quantity minus x and substitute that in for any x's in your given function, if you get the same thing, then you know that your function f of x is even. And a function that is even has symmetry with respect to the y-axis. A function f of x is odd if f of minus x is equal to minus f of x. So you take minus x, you have that take the place of any x's in your function f. If, after doing that calculation, you find that your resulting function is the negative of the function that you are given to start with, then you have a function that is odd. A function that is odd has symmetry with respect to the origin. There is no term, no other special term for a function that has symmetry with respect to the x-axis, because if there is symmetry with respect to the x-axis, then by definition that is not a function, because you have two separate outputs for a single input, and we can't have that if we have a function. So here's some examples of how we determine whether functions are even or odd or neither. Is x to the fifth plus 4x cubed minus 2x even, odd, or neither? So first thing you're always going to do in this kind of case is you're going to figure out what is f of minus x. So I'm just substituting minus x in for wherever there were x's in here. And then I'm going to raise these things to the appropriate power. Recalling properties of exponents, the shortcut way you can sort of handle this if you want is if you raise minus x to an odd power, then the sign that's out front of that term will change. If it was positive, now it's going to be negative. If there was a minus sign out front, now there's going to be a plus. And then if you have minus x raised to an even power, then the sign that's in front of that term will remain the same. If it was a plus, it's going to be a plus. If it was a minus, it's going to be a minus. So here, I have minus x to the fifth power. That's an odd power, so the sign out front will change. And same thing goes for here and here. Minus x cubed raised to an odd power, the sign changes, and minus x to the 1, an odd power, the sign changes. So I have minus x to the fifth minus 4x cubed plus 2x. And I notice that if I pull the minus sign out of these three terms, what I have inside of here is exactly what my function f of x was that I started with. So I find that f of minus x is equal to minus f of x. So once you find what f of minus x is, try then figuring out what minus f of x is. If it's the same, then you know your function is odd. If it's not the same, then see is f of minus x equal to f of x. If it is, then you know that your function is even. If that's not the same, then your function is neither. But in this case, f of minus x equals minus f of x. So in this case, our function here is odd. And just to clarify, a function is only ever one of these things. It's only even, odd, or neither. It's never none of them, and it's never more than one of them. You can't have a function that is even and odd. this one here, x cubed minus 4x squared plus 7x minus 2. Is this guy even, odd, or neither? Try this one on your own. See if you can come up with the answer. So find f of minus x. Then find minus f of x. Compare these two things. If they are the same, then you know your function is odd. If not, then compare f of minus x back to your given function f of x. If these two things are the same, then you know your function is even. If those two things aren't the same, then your function is neither even nor odd. So press pause now, try to figure this out on your own. Once you think you have the answer, press play, and we'll see if you were right. All right, so let's see if you came up with the correct answer. F of minus x. Here we have some things raised to even powers and some things raised to odd powers. So here, minus x to an odd power, the sign out front will change. Here, minus x to an even power, the sign does not. Here, minus x to an odd power, the sign changes. And here, just a constant, it's going to remain the same. So this is f of minus x. Clearly, this is not equal to f of x. We have different signs in these two places, so the function is not even. Let's see if it's equal to minus f of x. And minus f of x is this guy right here. You're just changing the sign in front of each of your four terms. Well, if you compare that sign there and that sign there are not the same. Since those signs are not the same, f of minus x is not equal to minus f of x, and thus we have to conclude that f in this case is neither even nor odd. So those were just a couple sample problems there showing us how we determine whether a function is even or odd or neither. We're going to move on to a very important type of function that is out there. It's called piecewise functions or piecewise defined functions. So what these things are basically, you can think of these guys as like Frankenstein functions, where by Frankenstein functions, I mean you take sort of bits and pieces of typical functions and you splice these guys in some kind of a format to make a whole new function. Algebraically, for certain x values, you'll have a certain thing being the thing that you plug your those x values into. Here's an example of what I'm talking about. So this here is an example of a piecewise defined function. The function f of x is equal to x squared if x is less than or equal to 1. So if you have to sketch a graph of this, and if you pick a number less than or equal to 1, you're going to be taking that number and you're going to be plugging it into x squared here. If x is greater than 1 and less than or equal to 2, then f of x will just equal 3. And then if x is greater than 2, f of x is just x. So just to get some basic practice here with evaluating these piecewise defined functions, if we wanted to know what is f of 4, what you would do is you would look at the x value that you're given, and you have to find the piece such that the x value satisfies that inequality. So obviously 4 is not less than or equal to 1. 4 is not between 1 and 2. 4 is greater than 2. So since 4 is greater than 2, it satisfies that guy there. So I'm going to take my x value and plug it into this piece here. So f of 4 is going to be 4. If I chose f of 1.75. Well, 1.75 is between 1 and 2, so it satisfies this guy here. So I'm going to take my x value, plug it into this guy, this piece here, and I always get the number 3 out. And then lastly, if I said f of minus 2, well, minus 2 is less than or equal to positive 1, so I'm taking negative 2, I'm substituting it in for the x in x squared, and I get negative 2 squared, or 4. So that is just the basics of how we evaluate these piecewise defined functions, or these piecewise functions. Here's what the graph of this thing looks like. If you picture just the graph of x squared, or you just picture the graph of just x, or if you just picture the graph of 3, then you'll see that there are shapes here that very much resemble those graphs. It's not the entire graph because we are only taking these functions here for certain x values, but it is the graph of x squared being used for some interval of x values, and the graph of 3 being used for some interval of x values, and then the graph of x. So that's what the graph of this guy looks like here. Try to graph this guy on your own. There are 4 pieces here. F of x is equal to minus x minus 8, provided x is less than negative 5. It's equal to negative 2, provided x is greater than or equal to negative 5 and less than negative 1. It's equal to x plus 1, provided x is greater than or equal to negative 1 and less than 3. And it's equal to 9 minus x, provided x is greater than or equal to 3. So press pause here. Try to graph this guy on your own. If you think you have a graph, then press play, and we'll see if your graph is correct. All right, so let's see if your graph was indeed correct here. This is what you should have gotten. For x less than minus 5, you have minus x minus 8. Between x greater than or equal to negative 5 and less than minus 1, we have negative 2. X plus 1 for x greater than or equal to negative 1 and strictly less than 3. And then 9 minus x for x greater than or equal to 3. Now, note that on this graph, where we have these dots here, note that some of these dots are filled in and some of those dots are hollow. The dots that are filled in indicate that we included that x value in the domain of that particular piece of my overall function. Looking here at x is equal to minus 5, we said that our function is equal to minus 2 when x is greater than or equal to minus 5. That's why we fill in that dot there. It's not equal to negative 2 when x is equal to minus 1, but the function is equal to minus 2 when x is less than minus 1. So that's why at x equals negative 1 here, for that same piece, we have the whole hollowed out. It's not filled in. So that's just a little bit of explanation as far as how the graphing of these things go. You have to be careful based on whether x values are or are not included in a particular piece. So these piecewise functions can actually come up in everyday situations. The following is a pretty basic and pretty understandable example as to how these guys can pop up. You have a car insurance policy that has a deductible of $1,000, if you are in a car crash, the car insurance company will cover damages up to $40,000, after which if you incur any damage on your car that exceeds $40,000, they're only going to pay $40,000. If X is the amount of damage to your car and Y, or f of X, is the amount of money that the insurance company will pay out, write a piecewise function relating X and Y. Now, given a word problem, given a situation like this, there is a little bit of common sense and a little bit of just basic thinking that does have to go into it. However, it's not too complicated once you actually talk it out and you reason it out loud to yourself. So, my piecewise function, f of X, here, going to have some different pieces here happening. So X is how much damage is done to your car. Well, you have a car insurance policy that has a deductible of $1,000. If you have damage to your car that is less than or equal to $1,000, then you are going to pay for that yourself, because you're not going to file a claim and have to pay your deductible of $1,000 if you have less than $1,000 worth of damage done to your car. You'll just pay for the damage and have it fixed on your own. So if X is obviously greater than or equal to 0 and less than or equal to 1,000, the car insurance company is not going to pay any money out. So that's just going to be a 0 for the value of your function, or for Y. They're not going to pay any money out. You're going to be paying all of that on your own. Once you hit over $1,000, the car insurance company will pay how much damage you have done up until the point where you are at $40,000. So if X is greater than or equal to 10,000 and less than or equal to 40,000, then if X is your damage and the car insurance company will pay out what the damage was, then the amount the car insurance company pays is just X. Lastly, if you have damage to your car that is greater than $40,000, then the car insurance company is only going to pay out maximum $40,000. So for X greater than 40,000, f of X, the amount that gets paid out, is just $40,000. And that is our piecewise function in this particular case. So we see that we can come up with a real life situation and come up with a piecewise defined function or a piecewise function to represent real life situations here. The last thing I want to talk about in this video is some other features regarding functions and their behavior. Specifically, I want to talk about maximums and minimums. A function f of x is increasing on an interval I if for every x1 and x2 in this interval I, with x1 being less than x2, then f of x1 is less than f of x2. Before we get to maximums and minimums, we do have to talk about what a function is doing: increasing, decreasing, or remaining constant. Now, everything I said here at the start of this first point here, that is a very long and technical and mathematical way of basically saying that as you move right on the x-axis, your function goes up, or the graph of your function goes up. So only really look at it as what's in the parentheses here. I provided the technical mathematical definition of what it means for a function to be increasing, but that's not so necessary. Similarly, a function f of x is decreasing on an interval I if for every x1 and x2 in the interval, with x1 being less than x2, then f of x1 is greater than f of x2. The long and complicated way of saying, as you go right, the graph of your function goes down. As x increases, the function or y values decrease, go down. And then lastly, a function f of x is constant on an interval I if for two x values with x1 being less than x2, then f of x1 equals f of x2. Again, the long and complicated way of saying as we move right, the graph stays flat. The function stays flat. Doesn't go up, doesn't go down at all. Now we talk about maximums and minimums. And the sort of combined or joint phrase for talking about maximums and minimums, at least the ones that we'll talk about in this course, are relative maximums and relative minimums, also known as local maxes or mins, and combined, these are relative or local extrema. So a function f of x has a relative or local minimum at x equals a if there exists an interval I that contains a such that f of a is less than or equal to f of x for all x in I. Again, very long and complicated way of saying this. Very shortly, we're going to learn a much shorter and easier way to identify a local minimum. Equivalently, that whole long, complicated thing there, we can simplify that by saying f of x has a local minimum at x equals a if f of x changes from decreasing to increasing at x is equal to a. So the function would be doing something like this. It is going down, 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 and then it starts to go back up. Something like that. And that point where it stops going down and then right away starts to go back up, that is our local minimum. Similarly, a function f of x has a relative or local maximum. Relative or local maximum at x equals a if there exists an interval I containing a such that f of a is greater than or equal to f of x for all x in I. Again, that's a long and complicated way of saying that we have a local maximum at a if f of x changes from increasing to decreasing at x equals a. So going up, going up, going up, going up, stops, flattens out, and then it goes back down. So that point where it changes, that would be our local maximum. So let's take a look at some graphs here. Here we have this arbitrary function f of x. And here we have labeled especially some local maxes and some local mins. We see here when x is equal to -3, the function is increasing, increasing, and then at -3, it stops, it flattens out at that one value, and then it starts to go back down. Since it changed from increasing to decreasing there, that is a local maximum right there. At x equals -1, we have a local minimum because beforehand the function is decreasing, decreasing, flattens out at that one x value, and then it turns and goes back up. So it changed from decreasing to increasing therefore making it a local minimum. Just like what happened at x equals -3, we have happening at x equals 2, increasing and then decreasing. And then just like what we had happening at -1, we have happening at +4. Function is going down, and then it goes back up. So note that it is possible to have more than one local min and or local max for a function. That certainly is very possible. How can you sort of think of local maxes? Think of top of a peak, top of a hill, king of the mountain, top of the mountain, something like that. How can you think of a local minimum? Bottom of a valley, bottom of a trough, or bottom of a swale, something like that. Those are nice little visual pictures, visual things to think of to relate to local mins and local maxes. This graph here, try this guy on your own. Try to figure out at what x values are we going to have local maxes and at what x values are we going to have local mins. So press pause, try to figure those out. Once you think you have the answers, press play, and we'll see if your answer is correct. All right, so let's see if you came up with the correct answers. We had a local max happening in 2 places. The local maxes are happening at -1 and at 4. You know, increasing and then decreasing there. And then local mins happening at -2, or sorry, at +2, and then at +6. The function is decreasing, decreasing, changes, it goes increasing. Here, decreasing, decreasing, turns, and then it increases. So that concludes this video on piecewise functions, symmetry, the different types of symmetry we can have, even and odd functions, increasing, decreasing, and constant functions, and then relative maxes or mins. Guys, if you have any questions, please feel free to reach out to me. Send me text, rocks through my window, shout really loud, messages up in the sky, whatever you have to do. Until the next video, take it easy, guys.